Have you ever wondered if there are absolute boundaries to what we can truly know about the universe, not because of technological limitations, but due to something deeply fundamental? In the quantum realm, there is indeed such a boundary concerning to crucial properties of any particle, its position and its momentum. You simply cannot simultaneously measure both a particle's exact position and its exact momentum with arbitrary precision. The more precisely you know one, the less precisely you can know the other. This intrinsic trade-off is famously described by the Heisenberg uncertainty principle. This limitation arises directly from the wave-particle duality inherent to all quantum entities. Every particle, like an electron or a photon, exhibits both particle-like and wave-like behaviors. When you try to measure a particle's position very accurately, you are essentially trying to localize its wave packet, which inherently makes its wavelength, and therefore its momentum, less defined. Conversely, to precisely know a particle's momentum, which relates to its wavelength, you need to observe a very extended wave, making its specific location uncertain. The act of measurement itself, by interacting with the particle, inevitably disturbs one of these properties as you try to pin down the other. For scientists and engineers working with quantum systems, this is not a frustration with imperfect instruments. It is a foundational law of physics that dictates what is physically possible. This means that when designing experiments or building quantum technologies, one must always account for this inherent trade-off. For example, if you need to know a particle's location with extreme precision, you accept that its future trajectory, dictated by its momentum, will be very uncertain. This principle guides the very design and interpretation of quantum measurements across fields like quantum computing and quantum sensing. This concept is deeply rooted in the mathematical structure of quantum mechanics, specifically in what are known as canonical commutation relations between operators representing observables. These relations show that position and momentum operators do not commute, meaning the order in which you consider them matters, unlike in classical physics. Furthermore, this principle is not unique to position and momentum. Other pairs of quantities, known as conjugate pairs, such as energy and time, also exhibit this fundamental uncertainty relationship. Understanding the position and momentum uncertainty pair helps us grasp the probabilistic and fuzzy nature of reality at the quantum scale. It highlights that the quantum world operates on principles profoundly different from our everyday experience. This isn't a flaw in our understanding or our tools, but rather a core feature of the universe, compelling us to adopt a new way of thinking about reality and measurement itself.
If quantum tech fascinates you, like, subscribe, and keep exploring with us.